Thank you for the really kind introduction. And I have to tell you all, it's been a real honor for me to get to work here for this semester. I'm looking forward to, I hope that this will start even more collaborations. I have basically a 45 or 50-minute talk, so I'll take questions throughout, but maybe we should save the really long discussion until, where I'm incredibly wrong or something. We'll save that discussion till the end. I just want to point out that the work that I'm doing at University of Delaware is very interdisciplinary, and I only have some of the co-authors here, and I'll try to recognize people throughout. So Fang is a material science student. She's working at IBM now. Luke is currently a material science student. Brian McCandless represents the people who I've worked with at the Institute for Energy Conversion, which is a big part of the solar effort at University of Delaware. Nicole Kodalak and Ken Schmieder, whose name isn't up there, are both from the Electrical Engineering Department. Dan Yang is also from the Material Science Department. Andrew Tepelkoff and Fang Young Tian are from the Chemistry Department. And so we have Chemistry and Electrical Engineering and Material Science in the Institute for Energy Conversion, and I've left off the Physics Department and the rest. So I think that's one of the spirits that I get here at University of New South Wales also, is that solar cell research really is a strongly interdisciplinary effort. So the talk that I'm going to do today is I'm going to cover three subjects. The first subject I'm going to talk about is this idea of Moore's law for photovoltaics. I'll go into that. It's a little bit controversial, but I like the discussion around Moore's law as much as I like the conclusions. Then I'm going to talk about how we can look at energy bands and heterojunctions. And then finally I'm going to end up talking about surface recombination, where surface chemistry really takes place. Okay. So on the first slide here, I think this is bringing coals to Newcastle, or whatever the expression is. I think everybody here realizes the importance of photovoltaics. This slide's a little misleading, right? So right now, even though photovoltaics are very attractive, it only contributes about 1% to the total energy input, depending, which area you look at. The idea is, though, that the solar energy keeps growing at 40% a year. And of course, if you do an extrapolation, which is always a bad idea, you can see that by the year 2030, all the world's electrical needs will be able to be met by photovoltaics. So this is a really big challenge. And of course, the sun only shines in the daytime, and so there's issues around this. But the point is that photovoltaics has incredible potential. And the more we think about it, the more clear it becomes. And so we actually presented this grant to the Department of Energy and to the National Science Foundation in the United States. And this is part of a proposal for engineering, a so-called Engineering Research Center that's led by Christiana Hansberg, a graduate of the University of New South Wales. And the idea is, and the National Science Foundation and the Department of Energy thought that was a good idea, and they've awarded this grant, which I'll talk a little bit more about. So one of the things that we presented is this idea of Moore's law, and it's actually pretty controversial in application to photovoltaics. Moore's law is usually applied to the integrated circuit field, and so the idea is that every 18 months or so, the chip speed will increase by a factor of 2, the feature size will decrease by a factor of 2. But 18 months is the timeline. And so Moore's law, of course, is not a law, it's an observation. And the electronics industry, the microelectronics industry, feels obligated to stay on this path. And so how do they stay on this path? The important part of the path, I think, and I made it red, is this idea of having a roadmap. What are the big technological hurdles? Do we need a high K? Do we need copper for the metallization? Do we need a low K dielectric for the back end of the line? And if you keep hitting these technical barriers, then you can stay on this 18-month paradigm, or on this 18-month model, which is not a law. And you can see on what I show on this plot here, which is Moore's law. This is just showing a bunch of technologies versus year, and showing the number of transistors per chip, which is again fits into this feature size idea. And you can see that this is it's on a log plot, is doubling about every 18 months, but the price per chip, or the price per bit, the cost per bit, continues to decrease, obviously with fluctuations there. So Quest is the name of the grant that we were able to get, and the approach that we're taking, so it's quantum electronics for sustainable, I forget what the S and the T stands for, but basically it's taking advantage of the quantum mechanics. And the idea is that we're going to look at high efficiency solutions to the problem. So we're not going to look at painting the side of the house with a solar cell at 2 cents a foot or something like that. What we're looking at is high efficiency alternatives. And let me explain why. On this plot here, actually this is a little bit out of order. On this plot here, we plotted the PV module price as a function of time. And the argument that we made to the funding agencies was that the price actually follows the embedded cost. And so if you look down here, we plotted here the cumulative PV module production. We could have plotted the total R&D budget. We could have plotted any other measure of how much effort's been put into the solar industry, and we would see this continuous decrease here. And so we argued, and I think the country of Australia and the National Science Foundation and the Department of Energy are buying this argument that this investment will continue to drive this price down to $1 a watt. Okay, so that's one of the things is that this is a good investment, you know, an excellent investment. The other part that I wanted to talk about was this idea of high efficiency. So if you look at the cost of a solar installation, this is just orders of magnitude rough. The cell itself is about a quarter of the cost. Okay, making the module is about half the cost, and the other half of the cost of the system is this balance of system, the wires, the land, the licenses, the inverter, all of that. And so it turns out that a lot of this balance of system costs and even the module costs sort of follow the area that's implied. So if I can use a higher efficient cell, even if it costs me more, I can decrease my module costs and my balance of system costs, and I'll end up with an overall price savings. And so you can make more sophisticated arguments, but basically this argument holds very, very well. So the idea is to use something that's sort of economically feasible, but still technically feasible, and aim for this high efficiency solution. Okay, the first subject I'm going to talk about is this band alignment in zinc telluride, zinc selenide thin film solar cells. And the story about the backstory here is kind of interesting. So Christiana Hunsberg and Professor Alan Barnett were fortunate enough to get a grant from DARPA Foundation on really high efficiency solar cells, and it had when the grant started out, it had a very, very broad focus. And one of the participants in this grant was a woman at MIT named Angela Belcher, who's an excellent sort of biological chemist. And what she had done is she actually developed a brand of bacteria or viruses that actually was able to deposit cadmium selenide quantum dots. And so the minute you start to hear about 2,6 semiconductors, you think, aha, solar cells. And so these little 2,6 quantum dots were great, but somehow we had to find out. And so she was part of this grant, but somehow we had to be able to measure, were these 2,6 quantum dots actually going to function in a solar application? And so this is going to sort of sum up that part of the grant that it was. But the general story, I think, goes much beyond that. So the idea here is we started out with cadmium selenide, and to make our device, we're going to put it on a cadmium telluride substrate and make solar cells. The problem is we had a heterojunction, and so we weren't clear what open circuit voltage we could expect or how did the bands align. And so that was one of our first approaches to this. So we knew pretty much what the structure of the cadmium selenide quantum dots was, so we knew where the valence band maximum was and the conduction band minimum. We knew the electron affinity. We knew the work function, so we knew where the Fermi level was. We knew all of those things. We similarly were able to measure a lot of those same parameters for the cadmium telluride substrate that we put down on the glass layer here. What we couldn't predict, what we had a very difficult time predicting, is you can see that in this picture with infinite cadmium selenide and cadmium telluride, that the bands don't line up. So what's going to happen when I bring them together? And clearly one material has a higher electronegativity than another. They're going to transfer charge. And so are we going to end up getting little spikes at the band lineup? Are we going to get cliffs? All of these things are going to affect the efficiency in the solar cell. The other thing we discovered, we thought that we might be the first people doing the zinc selenide, zinc telluride. Sorry, I've switched from zinc selenide, or cadmium. It's zinc selenide, zinc telluride. Zinc selenide, zinc telluride solar cells. And in fact, Book had evaluated a lot of these way back in 1977. Some of the advantages are that zinc selenide and zinc telluride are relatively non-toxic, tunable band gap with alloying, and you can use a lot of different growth techniques. So now we're actually switching, rather than using Angie's quantum dots, we're going to actually test out our situation with bulk materials, and then hopefully get back to Professor Belcher's quantum dots. Okay, so this is how we did it. We started out with a glass substrate, and we deposited indium tin oxide, layer of indium tin oxide. Then we did the zinc selenide layer, and beneath that the zinc telluride absorber layer, and then we made a back contact. And so we were actually able to make the solar cell as follows. The system that we used to make it in is something called closed space sublimation. So it turns out what you do in closed space sublimation is you'll have a small basket, say a small graphite, it's actually about that big, but a small graphite container, and over that you'll have your substrate directly over it. And then what you'll do is you'll flash the bottom very hot, and you'll directly transfer the zinc telluride in the first case from the bottom to the top. The reason that you do this rather than separately evaporating it is zinc and tellurium have very different vapor pressures, and so we would have had to calibrate it. If we were doing an evaporation, we would have had to work in high vacuum situations. In this system, we could have argon flowing with a little bit of hydrogen going through it, and we could stoichiometrically transfer the zinc telluride from the powder in the bottom of it to the top surface, which is held at a lower temperature. Similarly, especially for the case of zinc selenide, we did that too, because zinc and selenium have very, very different vapor pressures, and again, we were able to stoichiometrically transfer them from the powder down in the bottom of the graphite furnace to the top. And similar techniques actually are used, for example, at AVA Solar to make cadmium telluride solar cells. Okay, so this is a cross section of the solar cell we made. You can see the glass substrate on the bottom, the zinc selenide layer here, and then this whole part up here is the zinc telluride. The ITO is too thin to show up in this cross-sectional SEM micrograph. And so, here we show it. So you can see nice big crystals in the zinc telluride and very small crystals in the zinc selenide, which is probably not what you would want to make an ideal solar cell. So how are we going to analyze this now? How are we going to analyze the band structure? Well, what I do in my life is I do a lot of electron spectroscopy, and it's a very, very powerful technique. And so I think that this is the part of the talk that I think is sort of the take-home part, is what a powerful technique electron spectroscopy is. So basically, if I have a sample and I shine X-rays on the sample, I'll knock photoelectrons out. And what I do is I have a detector set up, and I can measure the kinetic energy of the emitted photoelectrons, okay? And each element emits the photoelectrons at a characteristic energy depending on how well the electrons are bound to that particular atom. And so I can actually figure out what the binding energy of my electrons are. If I do this in the laboratory, I have a fixed anode, so I'll have an aluminum anode or a magnesium anode or a copper anode. And so my light comes out at a specific energy. I measure the photoelectron energy, and I can go back and can figure out what the binding energy is just by a simple algebraic determination over here, okay? So every element emits photoelectrons at a characteristic energy, so I can tell what elements are there. The other thing is very simple quantum mechanics. Actually, Yvonne was giving a great lecture today. You can actually simply calculate what the cross-section, the absorption cross-section, what the probability of emitting a photoelectron is. And so by the intensity of the peak, you can tell how much is there. The really neat part of photoelectron spectroscopy, though, is if I have a silicon atom that's bound to silicon atoms, my photoelectron will be emitted from the say the 2p level, will be emitted at a specific energy. If my silicon is bound to oxygen that's relatively electronegative, it'll pull electron density off of the silicon, and my silicon 2p electron will come off at a different energy. So I can tell the chemical state. The other interesting thing, and we will get to this maybe a little bit at the very end of the talk, is it turns out one of the remarkable things about electrons is they carry charge. And so they're very good at detecting the charge, the electrical state of the matter. So if it's at plus 5 volts or minus 5 volts, I can pull that out also, so I can see what elements I have, how much of it is there. I can say what the chemical state of it is, and I can even say something about what the electrical potential that it's sitting at. Okay, so this is an example here of some antimony telluride that we looked at. And so you can see here in this peak, we're looking at electrons emitted from the tellurium 4D level. It doesn't matter, just a tellurium level. And we see 4 peaks in the spectrum. We see 2 peaks that are characteristic of the tellurium oxide and 2 peaks that are characteristic of the antimony telluride. And the shift that we see between semiconductor peak and the peak in the tellurium oxide is due to the fact that the tellurium is bound to the oxygen and the oxygen is relatively electron withdrawing. So we can tell the chemical state. The reason that we see actually two peaks here, it turns out this is sort of a quantum mechanical complication, is the electrons have angular momentum and they couple to the d angular momentum, and so we get the two peaks there. But that's the detail. No need to know that. But you can see that this shift here is sizable, so we can definitely tell the chemical state. Okay, so now we're looking at our zinc telluride. So remember, we started out with a piece of glass, we deposited ITO, then we close space sublimed our zinc selenide on the surface. And it turns out then we run over and we stick in our XPS spectrometer, and we're looking at the selenium 3D peak. And we see two peaks here. We see this relatively sharp one here, and that we can relate to the zinc selenide, and this peak over here, we see selenium bound to oxygen. And of course, if we take a big broad spectrum, we see an oxygen 1s peak also in our spectrum. The interesting thing at the zinc peak, we don't see any zinc oxide. So the surface of our, well actually we didn't know, we had to check and make sure it was on the surface. The surface of our zinc selenide that's deposited has a little bit of oxygen on. And so if we want to know where the valence band and the conduction band, the valence band maximum and the conduction band minimum of our material are, we want to get rid of this oxide. So we have a few ways to get rid of it. One of the ways to get rid of it is we could just sputter it with argon. So in all of these UHV systems, all these XPS systems, we have an argon gun, and we can just sputter off the top surface, and we can sputter the oxygen off and live happily ever after. Well, it turns out in our closed space sublimation system, of course, we don't have an argon gun, and so we can't do that. But what we do have is we have a hood nearby, and we have concentrated sulfuric acid at 50 degrees centigrade, and so we can take our glass coupon that has the zinc selenide layer on, dip it in, and you can see we can effectively remove the peak. And then we can stick it in and then deposit the zinc telluride on top of it. But let me show you a further complication. So we're looking at the selenium peak. So after we do the etching, it turns out that we have a peak that's in the slightly wrong position. So it turns out that what we've done is we now have a lot of elemental selenium that's not zinc selenide. And so what we have to do, so we've gone from a situation where we had zinc selenide with selenium oxide. Now we've done the etch, we've gotten rid of the oxygen. We're happy, except for now we have elemental selenium. So it turns out that what my student Fang discovered is that if you heat the sample up, and all you have to do is heat it up to 150 degrees C, where the 150 degrees C is actually a thermocouple sort of near the sample. It's pretty approximate, and just for a very short period of time, we end up with elemental zinc selenide. And this is the kind of thing that we could do in our closed space sublimation system too. Okay, so now we have a sample and we're ready to measure the conduction band maxima and the valence band maxima. How do we do this? Well, it turns out one of the important things that we have to do when we're making these measurements is we have to know where the electrical Fermi level is. And so what we do, and it turns out everything, the world has a common Fermi level. It has a common ground. So we ground our sample, but we want to make sure that 0 is actually at the Fermi level, that we don't have some kind of thermocouple in our system or some kind of charging problem. And so what we do is we actually measure the edge, the band edge of gold. Okay, so gold's a nice metal, has a nice sharp Fermi level edge. And how do we measure this edge? Well, it turns out that the X-rays that I'm making in my laboratory don't have a very good cross-section for looking at these edge electrons. A better way to look at it would be to use ultraviolet light. And a really good source of ultraviolet light is your local synchrotron. In the synchrotron, they spin electrons around basically at the speed of light. And every time they turn a corner, they emit all kinds of radiation. So we just pick off the ultraviolet radiation and we pick out one particular wavelength, and we can get tons of intensity. And so what we've done here is we've gone to Stanford, SSRL, Stanford Synchrotron Radiation Laboratory, and we're measuring, this is our Fermi level over here, okay. And I should be honest, remember how I said that the Fermi level was going to be at 0 volts? I'm going to tell a lot of approximations. It turns out that the detector doesn't work well at 0 volts, and so we actually put a little battery in back of it, and we knew exactly what our battery voltage is, and our battery voltage is minus 4.96 volts, and so that's why 0 is at minus 4.96. Okay, so now we're looking at our material, and we're looking at the conduction band maxima. Okay, and so here, this is the zinc selenide as it's deposited, and here at Stanford we were actually able to do sputtering in situ, and so we are able to end up with a pretty stoichiometric, and you can see the Fermi level is actually moved by about a good solid electron volt. Okay, if we look at zinc telluride, the conduction band maximum here, or the conduction band maximum here is up about a volt over that. So we now know the two valence band maxima for the zinc selenide and the zinc telluride, and presumably we know what the absorption cross section is. If we were at Yvonne's lecture an hour ago, you would have seen, so we know where the conduction band minima are, then we would be able to put the whole diagram together, okay? And so that's what I show here. So this is what happens if we use as deposited zinc selenide with the oxygen on the surface, and then we flash the zinc telluride on the surface. Here, what we measured at the synchrotron was the valence band maximum for the zinc selenide and the valence band maximum for the zinc telluride. We know what the absorption cross sections are, so presumably we know what the conduction band minima are, and everything else follows along. And so we know what the Fermi level is because we measured that with our gold sample right ahead of all of that. And the best voltage we can do, or the band offset, is 1.44 electron volts. The best open circuit voltage we could possibly get out of this is probably 0.4 of a volt less than that. Okay, if we clean the oxygen off first, we actually increase our open circuit voltage here by 0.2 of an electron volt, and we can see a difference in the position of our valence band maxima, as we saw there. And so we can apply this to all kinds of systems, is to look at the band alignment. The other system that my student Fang did at the same time as this is we were looking at thermoelectric materials. And in thermoelectric materials is you would like to have good electrical conductivity, but bad thermal conductivity. And so you put little small nanoparticles that electrically line up, but they scatter the phonons as they're going through the material. And so we had the same situation there where the bands, when clean material, lined up perfectly, but the bands of oxidized material did not line up, and the thermoelectric material did not work very well. So this idea has sort of general applications. We actually made solar cells. They were pretty crummy solar cells, honestly, out of these devices. But you can see we improved our open circuit voltage and our short circuit current. And I'm purposely not showing the IV curves because I think the fill factors were so bad that it's embarrassing. Okay. So the other part of the measurement is I've sort of been implying that we always know what the conduction band maxima, because we can do the absorption experiment in the laboratory, right? So if we know where the valence band maxima are, then we'll know where the conduction band minima are, just by looking at the band gap. EG will tell us that. Well, it turns out that one of the things that happens very often, especially in organic materials, but maybe some other materials that aren't so conductive, is I can excite the electron up to from the valence band up to the conduction band, but I get some pre-edge absorption. And what happens in this pre-edge is my electron here knows about the hole that it left behind, and it's got a Coulombic attraction between the two. And this Coulombic attraction actually is a binding energy. And so my light absorption may occur at a different energy than my one electron level, which is the one I'm interested in, is promoting a valence band electron into the free conduction band. So what we'd like to be able to do is to measure the conduction band minima, or the conduction band density of states. And the way we do this is we do a time-reversed XPS experiment. So what we do is we shine in electrons, rather than picking them off, we shine them in, they fall down into the empty conduction band levels, and they emit a photon. We were fortunate enough to get a grant from the National Science Foundation to build one of these, and so we're in the process of doing that. And this is what it looks like in my laboratory here in Delaware. But basically, here's the idea: here's my sample. We shoot the low energy electrons in. The photons come out, and they come off of a grating here. They're scattered off of the grating and detected over here. We can't use the photons are of such an energy that we can't use conventional optics. Everything has to be reflective because the lenses would absorb the light, and so it's all reflective optics that we have to do in this experiment. Okay, so we're in the process of building this. So this is a quick summary. I'll just tell you quickly the summary is we were actually able to make zinc selenide, zinc telluride solar cells. It turns out that part of the grant, we never actually did measure Professor Belcher's zinc selenide quantum dots, but we were able to build this. And the other thing is we now have routinely this ability to measure relative band alignment in homojunctions, whether they're in PV systems or thermoelectric systems or any other kinds of systems. And so that's very valuable. In the beginning of the talk, I I referred to this idea of making a roadmap. And so this is the roadmap that we proposed to National Science Foundation and Department of Energy a couple years ago. So it's not a really detailed roadmap. It doesn't have like red pages and green pages and yellow pages. But what we did is we selected a few of the really important items that were in the way of the development of really good silicon solar cells. And so I'm going to give two examples. One's going to be very quick because it's actually current work that's going on here. And one looks at silicon-containing tandems and heterojunction thin films and processes. And so this is work, there's a project being led here by Professor Alan Barnett and a whole large group of his students that are looking at gallium arsenide phosphide solar cells on silicon germanium solar cells. And the idea here, and the silicon germanium is grown on a silicon substrate. And so we have two industrial partners and a lot of students are taking part in it. Ellen and I had a joint student at Delaware who was taking part in it. And the idea here is that if I use gallium arsenide phosphide and I force it to fit the silicon germanium lattice, I can hit 40% efficient solar cells, okay? Of course, doing this in practice, you know, in the Shockley-Quasar limit. Of course, in practice, it's a lot more difficult to do that. And this slide is way out of date, you know, like 6 months, and so ignore any of the data and any of the results here. But so the idea here is we have a gallium arsenide phosphide solar cell and we have a silicon germanium solar cell here. But there's a lot of layers. Like one of the layers that's under current investigation is this window layer on the top. It's acting as a surface passivation for the gallium arsenide phosphide solar cell. There's other important layers where surface science comes in is when you're going on the 3,5, the gallium arsenide phosphide on the silicon germanium, is that you have to nucleate the proper 3,5 layer. And so that was one of the layers that Ken Schmieder worked with our 3,5 industrial partner is Vico. Amberwave is taking over the responsibility for the silicon germanium, the MOCVD of that, Alan Barnett, and Martin Diaz has now taken over this project, and Ken Schmieder was a student who worked with Alan and I on this project. But I put a few of the students who are here who are taking part in this. So we're trying to improve the tunnel junctions, the window layers, improve the integration of all of the devices. And so Martin Diaz and Brianna are being part of that. We're trying to optimize. We're now taking a very close look at the bottom cell, and so Shin and Dun and Anastasia are helping to all take part in that. And so there's still, even though we have a cell, we get yield, we get efficiency, we get voltages, there's still room for improvement, and we're hard at work on that. Where I'd like to spend the bulk of the rest of the talk addressing is this idea of surface passivation. Okay, so it turns out that one of the things that's very important in the integrated circuit business now is to use thinner and thinner silicon solar cells. Okay, and as you use thinner and thinner silicon solar cells, you have a higher density of electrons and holes, and so you have higher effective Fermi levels, and so you can actually get a device improvement. But one of the things that works against it, though, is now that our electrons and holes are interrogating the surface a lot more. So surface recombination is becoming more and more important. And so that's what we show in this plot over here is, let's see if I can get this. Here is, oops, I don't want to do the flashing one. Oops. Yeah, so what we've plotted here is the efficiency of the solar cell versus the cell thickness. Okay, and what we've done is we've looked at by changing the surface recombination velocity. And so you can see here, if you have solar cells between 10 and 100 microns thick, and you have crummy surface recombination velocities, you're not going to get a very high yielding cell. On the other hand, if you have this concentration of electron and hole pairs, you get high efficiency and you have very good surface recombination velocities. You can get very, very high efficiency out of these devices. For this group, I probably don't have to review this very much, but there's all kinds of recombination processes. In the bulk, there's radiative, trap-assisted, and Auger. The one that we're interested in for the purpose of this talk is surface recombination, is what happens at the surface. Okay, so in most of the talk that I'm going to be talking about is we're not actually making solar cells now, is we're going to be measuring the surface recombination velocity, and we're going to be doing this basically in a Sinton lifetime tester. So we're going to tend to, but not always, use float zone wafers to minimize the bulk recombination, make that as small as possible, so that what we're measuring is the surface recombination in these features. This, I don't think we also need this this slide here for this audience, but you can passivate cells with PECVD, silicon nitride, with amorphous silicon if you're making a heterojunction induced junction solar cell, with alumina, which I didn't put on here, SiO2 passivation, or in the case that we're looking at, we're going to be looking at this organic passivation, and we're going to try to understand why it's so effective. So basically, this is what happens when we're doing this quinhydrone methanol passivation. Is you take a silicon wafer, a piece of silicon, and you dip it in a hydrogen fluoride solution. The hydrogen fluoride solution etches all of the oxide away on the surface and terminates the surface with hydrogen atoms. So every silicon atom that had a dangling bond, it's now saturated with a hydrogen atom. And then we take the solution, this hydrogen terminated silicon wafer, and we dip it in a solution of quinhydrone, and I'll show you the structure of that on the next slide, in methanol. Okay, so quinhydrone, actually when we found out about this, we were introduced to this process from electrical engineers, and I was actually shocked to find out that quinhydrone is not really a chemical, it's a technical mixture of two chemicals. One is para-benzoquinone. The para means that these ketones are on opposite sides of the benzene ring, and hydroquinone, where we have the OHs on opposite sides. So it's about a 50-50 mixture of these two. What we do the HF etch. Well, first we actually do a piranocline, and then we do an HF etch, and then we dip it in the quinhydrone methanol solution, and it's all present in a stable plastic bag, and then we can take this over and we can take it to our Sinton lifetime tester and measure the lifetime. The results that we see in a lifetime tester, I think probably most of the people here are familiar. In a Sinton lifetime tester, basically you have your wafer or your sample is here. You flash it with a flash of light, and you have an inductor underneath. The inductor couples to the free electron carriers, and you measure the change of inductance in the inductor, and it's calibrated, so that will tell you how many free carriers you have as a function of time in there. And so it turns out that what we're plotting here is the lifetime as lifetime, not the number of free carriers, as a function of injection level. So injection level, our inductor tells us how many are there. We get the lifetime by looking at the slope of the number of carriers as a function of time. Okay, and so it's a little complicated, but basically, well, we've agreed to, and many have agreed to compare the carrier lifetime that we've determined from our Sinton lifetime tester at 10 to the 15th carriers per centimeter cubed. Okay, and so if we look at for N-type, always seems to do a little bit better than P-type for as far as lifetime, even for comparable situations. And our passivation is not stable forever. If we take it out of the plastic bag for an hour, and in this case, Bhumika, who did these experiments, took them out of the solution for about 20 minutes, and you can see that the lifetime went from 3.3 milliseconds to 2.7 milliseconds, and again, it cut in half on the P wafer. So one of the important things about this that we discovered is the surface preparation. And this went, I come out of the semiconductor industry, and so this went exactly counter to all of my intuition. The premier clean in the semiconductor business is so-called the RCA clean. But the RCA clean it's actually made, and I'm not sure if it was in foresight or in hindsight, but it doesn't matter. It takes care of hydrocarbons, metallic impurities, gets rid of the silicon oxide layer, ionic contamination, and particles. Each one of these steps is made to take care of that. So the premium RCA clean, it's SC1, standard clean 1, is a mixture of ammonium hydroxide, peroxide, and water at elevated temperature for 10 minutes. Then it removes the hydrocarbons and actually turns out the particles too, which I didn't put in there. It may cause some metal contamination and further oxidation. Then what we do is we immerse it in HF, and so that removes the oxide. Many of the ions in the oxide will also dissolve. But if they didn't dissolve, we then put it in HCl and peroxide. The peroxide will oxidize any metals. The chlorine will complex with it and remove any other metallic contamination. We'll end up with a thin characteristic oxide. So we've taken care of organic passivation or organic contamination, particles in the first step, and metallic contamination over here. Depending on where we put the HF, we can remove the oxide. This turns out is actually a pretty good place to go, but if we want a hydrogen terminated surface to go with, we'll have to do a final HF rinse over here. So this is the premier time-tested, the Class A #1 way of cleaning a silicon surface. There's no question. So the one that we were using the so-called piranha etch. And piranha etches are used after photoresist and things like that just to get rid of the organic contamination. So it was a mixture of hot peroxide and sulfuric acid, and basically you just get it from the entropy of mixing of the two, or the heat of mixing. And it cleans heavily contaminated wafers. Doesn't do anything about metals, anything like that. Then we chunked it into HF, a concentrated, not a dilute HF solution, concentrated HF in water solution for a couple of minutes to etch off the oxide. And I was working with Andrew Teplikoff in the chemistry department, who swears, he's a silicon surface chemist, he swears by the RCA clean. And what he did is he did an experiment called infrared spectroscopy. What infrared spectroscopy does is it looks at the vibrational modes in the surface. It absorbs infrared light, okay? And so if I do an RCA clean of a silicon 111 surface, I get one peak here. One mode, so I have a nice array of silicon atoms on the surface, one hydrogen on each, one going up and down, one mode. It's perfect, works just like you should. If I take my RCA clean, the RCA clean that we're using for our experiments, God knows how many modes there are underneath here. There's at least 3, but I think that's just because that's as high as we can count. But if we take these surfaces then and stick them in quinhydrone methanol, the RCA clean is always, depending on which wafer we picked and a lot of other things, as long as we're comparing to similar wafers, we're always doing a factor of 3 or a factor of 4 worse with our pristine, perfectly clean surface. We know it's pristine and perfectly clean when we grow a self-assembled monolayer on the surface. Okay, a self-assembled monolayer bonds on one end to the silicon, and we get this nice array of hydrocarbons all over the surface. And we can see in all kinds of different techniques, for example, in the infrared spectroscopy, that we get beautiful self-assembled monolayers on the RCA clean, and we get gunk on the surface of the long lifetime surface. Okay, and there's a bunch of other experiments that we did on that. But basically the idea is that the RCA clean surface is chemically the very best surface in the world. The piranha HF dunk is chemically terrible surface, but has a much longer lifetime. And that's very reproducible. We honestly don't understand why. And in fact, this carries over then when we start to do the lifetimes with the quinhydrone methanol. So when Bhumika was in my group and we were starting to investigate it, I was fortunate enough to have a friend of mine come and do a Fulbright fellowship with me from Turkey. And so he wanted to figure out what the heck was going on. He wasn't happy with all the Sinton stuff. He wanted to do the moleculars, sort of the molecular structure. So what he did is he took the infrared spectra after it was exposed to quinhydrone methanol. And it turns out that if you look at after quinhydrone methanol, you have a pristine, at least in photoemission, which has sort of a limited sample depth. In the blue curve, it's a pristine surface. If I do the same experiment with iodine, which works similarly to quinhydrone methanol, I have iodine on the surface, but a bunch of oxygen. And if I take my hydrogen-terminated silicon surface, I also see a bunch of silicon and carbon on the surface. So I didn't give anybody credit for this slide. I'll tell you who's credit for this slide. So I was talking to Nate Lewis, who's a professor at Caltech University, and he and I came up with this brilliant idea. We understood exactly why the surface was passivating with quinhydrone. It was the hydroquinone. And so what happened was we started out with the surface light that looked where's my light? Oh, here, there we are. There's our surface oxide. We did a hydrogen termination. Somehow or another, we got defects. We got junk on the surface that was acting as recombination centers. We reacted with quinhydrone methanol, and the component that was important is this hydroquinone that reacted with the species, and we formed this, and that was very stable until we brought it out into room air when the room air humidity came, and then we ended up with these OHs, which then acted as recombination centers. And so that's why it was unstable. And the reason that I'm giving Nate and I credit for it is because we were dead wrong. What my student Dan Yang did, and she said, no, let's actually do the measurement. We won't believe you. And so she compared the lifetime. She went and got purified, and she got very, very pure because we were also worried about contaminants in the benzoquinone or in the quinhydrone. So she did each one of these very, very pure, and it turns out that the lifetime of quinhydrone in this particular situation was 2.5 milliseconds. Benzoquinone was almost as good. Hydroquinone, you can see here, nothing, not a thing. We had some other chemicals laying around in the lab, so we tried that. You know, this again, it's a diketone. That worked okay. Hydrogen terminated silicon was actually pretty bad. The other thing that Dan discovered was that as we left it in solution, it got better and better and better. So whatever the reaction was continuing as a function of time. And so we're actually getting pretty confused. We know which guy is important. Again, here we've repeated these experiments with even more candidates. So things that just have a diketone like acetyl-acetonate are no good. We thought we understood it. So these are, Dan again did some very careful experiments. So she let the reaction go for a very, very long time and now had enough signal in photoemission to look and see, and I'll just cut to the answer here is when she did it with this, the benzoquinone molecule, the diketone, is she got 2 carbon peaks in a ratio of 2 to 1. The intense ones are these guys, you know, the ones without the oxygen. The less intense ones are the ones bound to the oxygen. There was actually there's no silicon showing up as an oxide, but there is oxygen present on the surface, and so she proposed that was the mechanism that took place. So let me show you at the end of last summer where we were. Is we understood that surface passivation of silicon with hydroquinone is very, very effective. It increased the lifetime carrier drastically. It really slows down, and I didn't go into all of that, the oxidation rate of silicon surfaces. Well, how does it do that? And we also know that crumbly prepared surfaces are better than well-prepared surfaces. So how does it do it? So what reaction? So when I was in Turkey on the Fulbright, I was working with an undergraduate there, Jarika Okiva, and what she did is she was trying to do density functional theory calculations. For those of you who don't know, DFT, as it's called, it's basically sort of a first principles calculation. You can see what reactions are possible, what structures are the most stable, things like that. It's very, very powerful for systems like silicon and carbon and oxygen. You wouldn't really want to use it for gold or copper or anything like that. And so what she showed is that benzoquinone will not react with a pure hydrogen terminated silicon surface. You have to put some kind of a defect on. And even though I'm out of Turkey and Jarika's going on to other things, she's still working on this to try to help us figure out what kind of defects are important. The other question we have benzoquinone is known to be photoactive, right? So if you shine light at benzoquinone, you can form all kinds of excited species, and it's these excited species that are taking place. Luke Costello and Macy Chen are working on that. We don't have an answer for that. Are protons in methanol important in passivity? One of the things that Nate Lewis did point out to me that was valuable was that he can actually react hydrogen terminated silicon surfaces with methanol. And so methanol is actually am I okay? Oh, okay. Can react with the surfaces. And so we were wondering if the protons in methanol were important. Another question is, why is the crummy surface better than the good surface, and at least in terms of lifetime? And it's almost certain that that we have charge centers. We have a more defective surface, we have more charge centers. So let's say that we have we have electrically charged defects on the surface. That's obviously going to act as a repellent for electrons recombining on the surface because of the Coulombic repulsion. And in fact, one of the things that Jarika has shown, and I probably shouldn't tell you on this slide, I probably should tell you that on the next slide, is that when you do get the benzoquinone to react with the surface, it does tend to form negatively charged centers. And so the negatively charged centers will repel incoming electrons, or will bend the bands anyway. And so we're also looking at generalizing this species. So one of the things is it's pretty clear to us that the hydroquinone bends the bands at the surface. And so I don't know about inducing a junction, but we're at least bending the bands at the surface. And that's more than likely what's improving the lifetimes. And so we're working with Arizona State, and Nicole Kodalak, one of my students, is looking at how much band bending do we get depending on the fictitious charge that we don't know is there yet. The other thing is Harry Atwater, Caltech is part of this Quest grant too, is he makes these silicon nanowires and he passivates them in organic. And so what he's taken to doing now is starting to look at the passivation with the benzoquinone kind of mixtures. I just want to show you what progress we made in the last half a year or so. These are the DFT, the density functional theory calculations that Derica is doing in Turkey. And so basically she's trying to mimic the silicon surface here. She's actually getting better at it since I made this slide, so she's using bigger slabs. The big atoms are silicon, the small ones are hydrogen. Here's our benzoquinone and there's the oxygen. And what she shows over and over again is that benzoquinone will react with a defect on the surface, where a defect's defined as missing an oxygen. Another thing that we discovered, in fact, this is more in the order of months old. I was working with Professor Şefik Suzer at Bilkent University in Ankara, and one of the things that we discovered is that if you have band bending at a surface and you shine, actually it's not all that intense, shine a laser on the surface, is that we can unbend those bands by generating a bunch of charge carriers. What they'll do is they'll flatten the bands as long as we generate charge carriers at a faster rate than they can recombine at the surface. And so the interesting thing about that, there's two interesting things about that. The first interesting thing is that we can probe, now this is from a surface scientist point of view, we can probe band bending at an interface much deeper than we can test with our photoemission. Photoemission, the photoelectrons are only coming from the top 2, 3, 4 nanometers. We can sample interfaces as deep as a micron below the surface just by shining light on the surface and looking at the shift in the energies in these surfaces. The thing that we wanted to do, because I was in the chemistry department that semester, is we wanted to do chemistry with it. And so the first idea I had, I'm taking credit for all the bad ideas, was I thought, well, look, we can change the surface energy by half of an electron volt just by shining a laser at it. Surely the contact angle of water or something like that will change, and we'll be able to detect that. And so we did the experiment. It kind of changed, but it turned out that what it really did is accelerate the oxidation. And then if you go and it's not even a first principle, if you do a simple calculation about the change in the thermodynamics of the surface, you expect a contact angle change of about 1/10 or 100th of a degree, which is a little tough to see in your microscope. The other thing, though, that we're doing is if we straighten out the bands on a p-type surface, is that we're going to end up with this big supply of electrons. And the really neat thing is, and that's one of the reasons why I was really glad to come here, is we have this supply of electrons, and they can reduce ions at or species at the surface. On the other hand, if I take an end surface, I have a supply of holes, and they can oxidize things at the surface. So the hope was, the hypothesis that I had 2 weeks ago was that what was happening is that on a P surface, it was reducing the benzoquinone, and that was reacting with the surface, and that was creating the lifetime. And on an N-type surface, the hydroquinone would be oxidized, react with the surface, and increase the lifetime. And in fact, what we saw is we're now being careful. We're keeping track P-type, N-type. Benzoquinone is the only species that does a lot of passivation. The other thing that we've been able to answer is that on these surfaces, that if we don't use methanol, if we use something like diethyl ether that has no proton on the surface, that benzoquinone will eventually passivate the surface, but takes much longer on the surface. So as usual, I mean, that's why we have hypotheses. Luke, Nicole, and Chen have shown, I think, that it's not a simple redox reaction and that protons are important. This is the class participation part, because you guys now get to tell me what I'm going to do next to try to figure this out. In fact, I'll be here for a few months. Let me give my acknowledgments. Surface chemistry, you can see, is actually very, I don't know about crucial, but I think it's a good advantage, and understanding the materials is very important in making good solar cells. Let me acknowledge some of the important people in this work that didn't get good credit. Chris Hunsberg and Stuart Bowden are both at Arizona State University, and they're both graduates of University of New South Wales. Alan Barnett is right over there. Conan Weiland is one of my students, and he works at National Synchrotron Light Source now for NIST, and he's been very helpful in a lot of these synchrotron measurements. Bhumika started the quinhydron experiments. She's at Micron. Şefik Suzer and Derica Akiva are at Bilkent University, who I worked with last semester as part of Fulbright, and Ulrika is actually helping Derica. Ulrika is a professor at Bilkent, and she's working with Derica to do the DFT. And the funding we've had is from all over the place. We've had National Science Foundation grants, University of Delaware, Fulbright Foundation, and 2 DARPA grants have contributed to this. So on that note, thank you.
Well, we have plenty of time for questions, at least 5 minutes, but maybe a little longer.
Actually, we have 2 months for questions. So. Oh no, too much chemistry? Yes.
Thanks very much, Bob, for that interesting talk. I want to come back to the telluride selenide materials and your mention of the potential for thermoelectric properties from them as well.
Right,
so
right.
You said that if there's a good line up of the bands, then you can have good electronic properties, good electron transfer, but good scattering of the photons. And you said that it didn't work too well because the bands didn't line up that well.
Right.
But what did you look into the ways to optimize the scattering of the photons, and so hence optimize that aspect?
Yeah. So actually, I was very. What we were doing is we were growing very thin monolayer or very thin layers of one material A, material B, and it wasn't zinc selenide and zinc telluride. One was the antimony telluride was for that case, and I don't remember what the other one is right now. And we were growing very thin layers, and the idea is and we're looking at transport basically along the grains, and it would be very difficult to keep a phonon going along the length of the grains, but we're still able to get good electronic conduction, was the belief. And so that's what we were trying to build these microstructures to.
And did that aspect work, the phonon confinement in those layers?
What's that?
Did the phonon confinement in those layers work, or were you able to ascertain that? Or?
No, what we did, actually all we did is we measured it. The way we measured it is with this reflectivity measurement, right? And so you hit it with a flash of light, and it gets hot, and you look at how the reflectivity changes, and that tells you, how quickly does it dissipate. Tells you something about the phonon, the heat dissipation. And so that's all that we did, And so we guessed from that measurement, what was going on with the phonons.
Interested to do some Raman on it and see whether the Raman, you could see some
that's right.
folded Raman modes.
That's right, yeah, and so actually I'm much less familiar with Raman, but it looks like a very, very powerful technique that I should work the learning curve on. So I know, like, the Raman for graphite and graphene and diamond and so forth.
But it should give some doublets appearing, particularly in a essentially what you've got a quantum well type nanostructure there.
Yeah.
Yeah, so that would be very interesting.
Oh, yes.
Most of the electronic device made on the silicon 100 surface, but all the treatment surface to be made by the on 111.
No, actually I wasn't very careful. No. Well, the reason is as a surface chemist, I love silicon 111, right? Because you get these nice arrays of silicon atoms and with one mode. But in fact, actually, I wasn't very, very good. These last set of experiments I showed were all on 100 surfaces. And I should have labeled that. In fact, I just got the email this morning about what the doping density is, and the orientation and everything. And so I'm not going to dig up that email, but it's not enough to call them N-type and P-type. All of these surfaces are 100 surfaces, and they're not float zone. They're Tucholsky wafers, and they're on the order of 10 ohm centimeter. But so the reason, and that was one of the things that I wasn't very good about in this talk, was we were switching from one set of samples to another set of samples. And when we were trying to do the very basic FTIR, the Fourier transform infrared spectroscopy, we were using silicon 111 surfaces then, because the FTI, the modes, the vibrational modes, are very, very easy to recognize in that situation. And this hydrogen stretch modes on the 100 surface are more complicated.
Any other questions?
Yes?
About the stability of the passivation layer against temperature. So in your solution, after you take out the solution, what's the stability?
You know what? So we never measured it as a function of temperature because we were honestly a little depressed. You saw that we were actually it decreases over the periods of 20 minutes and hours and things like that, and so that was going to go from bad to worse. I guess it would be worthwhile in understanding what the mechanism is for the oxidation of that surface, but we've never done that experiment. Yes?
Do you have any idea of the injection-dependent surface passivation of the surface?
Of the what dependence?
You take the injection dependent, so with different carrier densities.
Yeah.
Did it change between N and theta?
Yes, but we should talk about that offline because we're confused.
Now, due to time constraints, we have to finish here. So I would like to thank Professor Opila again, and thank you for coming to the seminar.